Okay. The plan for this week is to cover special relativity, specifically like the stuff some of you guys may not have covered in your modern physics class, which are invariance, Lorentz transformation, and four vectors. Okay. And hopefully we'll do the pre-review for this week's homework at some point in class also. So we're scratching that because of the storm. And we're going to see how we can construct invariance and out of these things called covariant and contravariance. So these are kind of like fancy words for like things that, varies or not or anti-varies. So we'll see how that comes about. And I'm hoping to start a little bit of quantum mechanics, so you get a little review of wave function and Schrödinger's equations on Friday. And then next week is we're going to be diving into all the quantum mechanics stuff that we need in order to get to do particle physics. Okay, so special relativity is published in 1905 by this guy that some of you guys might know. Actually, this is known as the miracle year because this is when Einstein actually published 4 world-changing papers. So it's like, I don't know if he was just saving up all the stuff and then just sending it all out at once, or he was just like, very inspired while he was working at a patent office. But the reason I noted this is that his paper, well, it's going to be in German, but translated to English is actually extremely readable to undergraduates. So if you just read that, his paper is actually titled "The Electrodynamics of Moving Bodies." So it's based on electricity and magnetism. You can just read it and then say, oh, if your things are moving like this, and you make these 2 postulates of special relativity, is that, hopefully this makes sense, right? Law of physics is the same in all inertial frame. Inertia means a non-accelerating frame, meaning you're not applying acceleration to that particular frame of reference you're doing, okay? The Earth rotating around we on Earth rotating around on the surface of the Earth, not rotating. As the Earth rotates, we follow it, okay? We are actually not technically an inertia frame, but the acceleration is not great enough to affect a lot of experiments. But this is the reason why, for example, hurricanes and tornadoes happen, because we are actually not an inertia frame. We're actually in a rotating frame. And so there's this thing called the Coriolis effect that actually creates storms. The other thing is that this was not an easy thing to postulate at the time. The speed of light in vacuum is the same in all inertia frames. So this is at the time in 1905, people were building experiments to try to measure the speed of light in different frame of reference. The more famous one is called the Michelson-Morley experiment. This is actually an experiment that took place at Case Western Reserve University, right? And I actually worked there for a couple of years, and I actually went down in the basement and actually see where Michelson and Morley did their experiments. And it's a nasty experiment. It involves like mercury and stuff like that. They probably pour into the ground afterward, poison the whole place, but not. but the idea is that where the way they were trying to measure the speed of light changing in different reference frame is that, well, if you have the sun, right, and then we on Earth is rotating around the sun at a pretty high velocity, right? If you have an interferometer, right, that has the equal length on each side, the light is going to bounce back and forth in that equal length in the inertia frame, okay? But if you're moving towards the right in this particular part of the orbit, what's going to happen is that the light will actually come back slightly sooner, and so you have these fringe shifts. And those of you who are taking my experimental lab will get to play around with this actually. Okay, but this is not a, the speed of light being the same in all inertia frame is not a given. Okay, Einstein postulated this, and there's evidence for this. When you take electricity and magnetism in general physics, sometimes you run into these constants called epsilon naught and mu naughts, and those 2 numbers add up, they multiply them together, and it's actually equal to like square root of the speed of light. It's not coincidence. It's basically, think of it as like kind of like the electric and magnetic coupling of light to free space. And that's why those numbers come out to be exactly the speed of light. And I don't know if Einstein actually got inspired by that fact or not, but that's actually sort of a interesting tidbit that, assuming that postulating the speed of light is the same in all reference frame is not just a given to him. Okay. But now that we know that, we have tons and tons of measurement that shows that the speed of light in vacuum is the same as long as you are in a non-accelerating frame. We can apply these and see the consequences of it. Okay. So one of the consequences is that, well, if you are in some inertia frame sigma, so the book uses the sigma to define each of the moving frames, okay? And then you have a second frame, okay, sigma prime, that is moving at some speed v relative to the original frame, sigma, okay? You can define some, funky axis, right? So let's say the horizontal, we're gonna call that the z-axis, okay? And then the vertical axis, let's just call that y. So both of these are associated with the non-moving frame, okay? Since the frame of reference for sigma prime, the inertia frame sigma prime is moving, right? This vertical axis here is going to move along with the frame at some velocity v in the z direction, okay? So whatever measurement you make in, get rid of this box up top, whatever measurement you make in the non-moving frame, okay, it's going to have some coordinate, and this is a vector, right, in general, okay? And you're going to measure it at some time. So this is actually known as an event because it gives you the time and position vector, right, R, right? And you would measure that, right, in your sigma frame, okay? But someone, let's say, sitting on a train or flying on a spaceship is moving in the sigma prime frame, okay? They would have a different measurement of both time and position vector, okay? And it's very easy to see this, right? Along the z direction, these lines are not even the same, right? So you can actually see that you have to change your coordinate system between the two frames in order for you to make the same measurement, okay? Okay. So since any measurement has to obey the same laws of physics, any measurements you make in each inertial frame has to obey the same laws of physics, right? So for example, if you apply some force on this particular mass here, right? That mass has some mass m, they will experience the same acceleration, right? So the acceleration, right? The force in that particular frame, right? It's going to be mass time acceleration. But if you move to the other prime frame, right? You will have a different mass times acceleration, but these calculations should be all the same, right? You don't have to change the laws of physics just because you're on the train or something like that, okay? And then the fact that the speed of light has to be the same in both frames. Let's say I'm shooting this little, I shoot off a little light beam, right? Photon beam, right? Into this point as some t equals to 0. And I'm going to define it so that both t and t primes are 0. That's when I shoot the beam, right? And I'm trying to figure out how long does it take for the beam to reach my my position r here, okay? In this case, right, in the non-prime reference frame, you can calculate this because the speed of light is c, and therefore the speed times the speed times the time will give you the distance, right? So if you're driving on the freeway at 55 miles per hour for an hour, you will drive 55 miles, right? So those are just kinematics that we can calculate. Okay. The special thing is that, well, of course, the same thing has to happen in the prime frame, right? The speed of light is the same in both frame of reference. So therefore, right, c prime, t prime, right? So all the moving frame is, we're going to put a little prime on it just to confuse it with, sometimes, I think calculus, in calculus classes, they use prime as derivatives. So don't think about that, okay? Think about this as different reference frames, okay? It's the same, right? I'm just copying this equation down, okay? The postulate makes it so that, right, the c in one reference frame is exactly the same c in the other reference frame. The speed of light is the same in both frames, okay? That's the thing that's different, right? So So there is no C prime, there is no C double prime, there is no C triple prime. The speed of light is the speed of light no matter which reference frame you're using, okay? What you can do is then solve these equations and squish them together, and then you will have this equation down the bottom, 2.2, okay? Okay. And therefore, the speed of light times the time square minus, all the position stuff, okay, equals to the speed of light times t prime and all the position coordinates squared in the prime reference frame also, okay? It's just, squaring both sides and then equating them, okay? Okay. The stuff on the left and right-hand side here are known as invariants, okay? Okay. The reason they are invariant is that, wait, I went from coordinate system sigma to coordinate system prime, right? The equations are actually the same. These, whatever you add, okay, the equations are different, right? Because one has prime, the other one doesn't have prime, okay? Whatever number you calculated from this, let's say you calculated the left-hand side here and it's equal to 10, okay, whatever, some units, okay? Right? In the prime frame, this value is also equal to 10, right? Right? Because by definition, equation means that it has to be equal to each other, right? Okay, so the 10 is about, it's probably not a proper example. All right, this is probably a space-like interval, actually, which will be things traveling faster than speed. Don't think about that, okay? But does that concept make sense where if you change reference frame, that number stays the same, right? No matter what reference frames are changed to, that number has to be the same. Okay, it's kind of like, okay, by just forcing this particular construction of an equation. See, people are just staring at me. People on Zoom are probably staring at the screen also. Okay, this will become a little bit more clear. This value is actually, this number is actually called S, but we're going to see that later. Okay, the consequence of this is that you can do these things called, you can relate the unprime coordinates, T's, to the prime coordinate system, okay? You can figure out how to translate between the two, okay? And this is one of the, I think, either the first or second homework problem where the equation 2.2 is satisfied if T prime is equal to this gamma times T minus V over C squared times Z, if the reference frames are only moving along the Z direction relative to each other at some velocity V. Okay, that's how fast they are moving. Okay, since the reference frame are only moving relative to each other along the Z direction, right? So let's do this, right? Z prime, Y prime. Okay, the Y coordinate doesn't change, the X coordinate doesn't change because they're in the same place. Okay, it's the Z coordinate and the time coordinate that are, okay, transforming when you transform from one frame reference to another, okay? Okay. And then this equation here is also has this gamma factor in it, of course, okay? And this gamma factor, I think we discussed this last week a little bit already, is 1 minus beta square, all to the -1/2 power. If you don't like looking at that, it's just the same thing as writing this, okay? Like that, okay? Ivan?
So when switching inertial reference, so let's say instead of this being T prime, they want to switch T, would the sign change? So
yeah, so
it's going to the T prime is going in the positive x direction.
Right.
The opposite.
Right. When T prime is going in the is moving to the right along the Z direction, then you have the minus sign of V. So yeah, you're right. You're gonna see the equation soon. Maybe I put it in there or not, but you're gonna, if you're translating from the prime frame, translating from the unprime frame to the prime frame, yeah, that velocity will flip sign, so you have a positive V instead of a negative V. Okay. Okay. So in the homework, you get to plug this equation in and then figure out that it is true that having T prime being this and then Z prime being this will allow you to satisfy equation 2.2. Okay. Okay. So once again, so we still have C's down here, right? Remember last time we wrapped up with that. Oh, why not just make C equals to 1 to make things simple? Okay, we're gonna switch to natural units at this point and just make C equals to 1. So all these C's just turns into 1. Oh, there's only one C here, right? And then so basically beta is going to be V, but V is going to be defined as kind of like fraction of the speed of light instead. Okay, so therefore these equation whatever 2.25 between the two, right, just turns into this. This is why they probably didn't label this. Okay, so instead of dealing with 4 separate equations, this is where having systems of equations or systems of linear equation, and then this is going to turn into this thing called linear algebra, right, where we're going to start writing matrices makes more sense. Okay, so so I think some of you guys may not have covered linear algebra or covered linear algebra in like a week or two in your in some of your classes, in your differential equation and linear algebra classes or mathematics class. So let's just practice how we deal with these matrices, okay? So this matrix is going to be this crazy capital or bolded X prime, okay? And what's on the right-hand side is this other matrix here. Well, they're all kind of tensors, but okay, so let's call this a vector. And then you have this, I think it's actually easier for me to just write it and talk about it. So the left-hand side is some vector, okay? So the left-hand side is some vector, and you have this thing called lambda, so it's a capital lambda in Greek, okay? And this is actually a matrix, okay? And you're gonna do a matrix multiplication to it to the non-prime frame, okay? So the idea is that this equation here with these giant matrices, okay, vector, matrix, vector, is the same as this equation, okay? So let's just show that that's true, okay? So to do matrix multiplication, what you do is you take the first row and you multiply that by the column that you're multiplying by, but one element at a time, okay? So you take gamma, okay? So this one here is, right, T prime, this row here is called T prime. It's going to be equal to this first element here, multiplied by the first element here, gamma T, okay? Okay, I'm going to circle a different color for the next part, okay? I'm going to take 0 multiplied by x, right? So anything multiplied by 0 is 0, and then another 0 multiplied by y, okay? But the last point here, right, that's going to be different. Let's do that in green, okay? I'm going to take negative gamma beta, multiply that by z, okay? Negative gamma beta, multiply that by z. Does that make sense? How many of you guys never seen this before? Multiplying matrices to vectors. Anyone on Zoom never seen this before? Okay. So massaging this a little bit. So feel free to say so if you haven't seen this. We'll practice a little bit more of this. And I have you guys do some homework on this anyway. Right? Massaging this a little bit, we get gamma times T minus gamma beta Z, right? Which is the same thing as if we factor out the gammas, right? Then we get gamma T beta Z, which is exactly what you have up here, right? On this side. Okay. All right. Should we practice one more time with Z prime? Let's practice one more time with Z prime, okay? Z prime. Hopefully you guys can see. Actually, let's practice at least one of the non transforming ones, okay? So X prime, right? So X prime in this matrix here, right? I'm going to multiply this row by this entire column, okay? 0 times T is 0, okay? 1 times X is X, 0 times Y is 0, 0 times Z is Z, okay? So that's why this equation came out like that, okay? All right, let's practice so the Y prime is going to be the same. Oops, not X, Y prime is going to be Y, okay? The Z prime, right? That's the one that's more interesting. I'm taking this row, multiplying by this entire column, okay? So the first element multiplied by the first element here. So gamma beta times T, okay? And you have 2 zeros multiplied by the X and the Y, so those just come out 0. And then I need to fix the sign. And then so gamma times z, that's the last element, right? Okay. And we're going to do this. I'm going to factor out the gamma, reorder things, and hopefully we get exactly the same equation as up here, right? Okay. Okay. The idea of these matrices is to just kind of reorganize the information, right? Okay. We haven't got anything new, right? The four equations in 2.3 represent the exact same information as 2.4. Okay. And the reason we do that is that, well, now I can write x prime equals to lambda x. Okay. And that's just shrink things a lot, right? So I don't have to deal with like 4 separate equations. Okay. Okay, so I think as Ivan already mentioned, if you want to transform from the prime to unprime, meaning write the equation that are going to give you t equals to gamma t prime plus beta z, and then x, well, x is going to be equal to x prime, y is going to be equal to y prime, and then translate z equals to gamma equals to z prime plus beta t. Okay. The only difference between translating from the unprime to the prime coordinates and then the prime to the unprime is just switching that sign of the velocity. When you switch the sign of the velocity, the beta switch sign, right? Because beta is basically v over c. Okay. And maybe I should assign homework to double check this. If you multiply the two matrices together, actually, let's just do it together. Okay. If you multiply these two matrices together, this is going to turn out to be a interesting exercise, but the problem is that I know what the answer is. And the answer turns out very what do I call it? Very, you would think this is going to be complicated, but the answer is going to be very simple. That's the problem. Okay. If you want to multiply two matrices together, 1, 0, 0, you line them up like this. Gamma, beta, 0, 0, gamma. Okay. You do something that's very similar to what you did in the matrix to vector multiplication. I'm drawing these lines. You don't have to draw these lines just so it can kind of demarcate each of the elements. Okay. Oops, that's not a good line. It just kind of goes up. Okay. Okay. So what I'm going to do, so this is element 0 or row 0, colon 0 here, right? So to figure out what this number is, what I'm going to do is I'm going to multiply this entire row with this entire column, one element at a time. Okay. So gamma times gamma is going to be gamma squared. Okay. Okay. A bunch of zeros here, so we don't have to worry about that. And then we're going to add to that, well, actually gamma squared minus times beta squared. Okay. Because this is this multiplied together, right? Okay. Okay. So let's not simplify things first. The other elements is going to be 0. I'm just going to tell you which one are going to be zeros. Okay, you can check that. Okay, and we'll find the ones that are not 0. Okay. Okay. Let's do a green marker here. Okay. Okay. To figure out what this element is, we're going to multiply this row with this column, right? It's column 1. Well, the second row with the second column gives you the second element on the second row. Okay. Okay. So if you multiply this out, does anyone know what that answer is going to be by looking at that multiplication? It's going to be 1. Okay, great. Similarly, if you do the third row and third column, you're going to get 1 here also. The last one is always the more interesting one, right? So I'm going to multiply this row with this column. Okay. And then you're going to end up with minus gamma squared beta square, right? And then this last piece gives you the plus gamma square. Sorry for the bad writing. Okay. Okay. So these two values are actually the same, but does anyone have an intuition what that number is?
1.
Yeah. Yeah. Why is that equal to 1? What should I do to prove that is 1 right now? The next line. What should this equal? What should I do now? Anyone? What should be in the parentheses if I factor out the gamma? 1 minus beta square. And what is gammas? Gamma is 1 over 1 minus beta to the 1/2 power. If you square it, right, this just gives you this first power. You plug this in here, it's just 1 minus beta squared multiplied by, divided by itself. Okay. So all these stuff is also 1, 1. Okay. Hence, right, if you multiply a matrix to its inverse, you get what's known as the identity matrix. The identity matrix is just zeros everywhere and ones along the diagonal. Okay. Okay. And sometimes you'll see this where I just write a giant O where all the other elements is just zeros. Okay. Okay. So these matrices are known as inverse of each other. And hopefully that makes sense, right? If you transform from sigma to sigma prime coordinate system and then do the inverse transform back to sigma, the answer should still be whatever your original coordinate system is, right? Okay. So the identity matrix is like multiplying, it's like matrix multiplication version of a number 1. Okay. Multiply anything by 1, you get the same number. Okay. Okay. So this is nice. Okay. Okay. But notice how much space this took, right, in order to do that matrix multiplication. So what Einstein came up with is known as the Einstein notation. Okay. Okay. What we're going to do is we're going to first basically treat time and space the same. And we're going to shove them into these things called a 4-dimensional vector called 4 vectors. Okay. I'm going to be typing these things called 4V. So when you say 4V, that means it's the 4 vectors also. Okay. We're going to do, instead of defining, this as a column vector, we're going to define this with just x mu. Okay. And x is not the spatial coordinate x. X just is the 4 vector version of x, meaning that it will have time, x, y, and z in it. Okay. This is very confusing because the x is in here also, right? Okay. Where this letter up here, mu, okay, is upstairs. It's not the power. It's not x to the power of mu. Okay. And this is actually just the index of this particular vector. Okay. So if I say as for x 0, and we're going to start counting from 0. So mu goes from 0, 1, 2, 3. Okay. X of 0 is going to be the time coordinate. X of 1 is actually the x coordinate. X of 2 should be what? Y. And then x of 3 is going to be the z coordinate. Okay. Okay. All right. Be a little careful, right? The notation is that you have these Greek letters on the upper right of your 4 vector. Okay. And also be careful here, right? This is not bolded. Okay. Not bold. Okay. The reason this is not bold, because this technically don't represent a vector. It represents pieces of a vector depending on what mu is, right? Right. If t is equal to 10, x is equal to 20, right? Each of these mu's will represent a different number, right? They're just really numbers. Okay. Okay. And since the index is upstairs, this is called a contravariant vector, 4 vector. And we're going to see why it's called contravariant versus covariant, and how that comes about. after a couple of more, hopefully by the end of lecture today. Okay. So instead of writing that big lambda equation up here, right, in equation 2.6, right? Once again, what we're going to do is we're going to define this so that we can go ahead and make x, let's say x mu prime, x mu prime, right, equal to some matrix, okay, multiplied by this 4 vectors that we just defined, okay. X, I'm gonna have to use the change to a Greek letter nu, because what's going to happen is that we're going to have mu down here, nu down here, and nu downstairs. Okay. And that matrix is defined by this big giant box. Okay. It's the same matrix as before, right? But we're just denoting it with mu's and nu's instead of just then rather than without it. Okay. So remember that mu goes from 0, 1, 2, 3. Those of you who have, done programming with like arrays and stuff like that, hopefully this will makes it easier. So nu also is another Greek letter. So any Greek letter, we're gonna see that the index runs up from 0, 1, 2, 3. Okay. So mu equals to 0. Nu equal to 0 represents this number here. Okay. Let's pick another one. Mu equals to, let's see. I'm gonna make sure I'm doing my notation right. 3. So when I do that, now mu equals to 0. Is it row first or column first, Alex? You remember? Just want to make sure this is right.
Row is first.
Row is
in programming.
But this is upstairs. So this will go along with the time coordinate. Yeah, this is with the time coordinate. Yeah, you're right. Okay. 3, 0. Okay. So you can basically map out where, if you have this matrix somewhere, you know what each of the elements are. And these mu's and nu's are representing which element you're talking about. Okay. Right. The mu is the row, the nu is the column right now. Okay. Be a little careful, but it depends on what the position is. It's not that mu and nu are special. It's that mu is upstairs and then nu is downstairs. That determines it.
So if it is mu is the row, we are at row 0 and column 3.
Oh, yeah. Yeah, so it's actually reversed in compare program. Yeah. Okay. Yeah, so this is a lot of like little notational index. So what happened is that, right? This allows you to, instead of dealing with a matrix equation that looks like this, right? Well, actually, I have it down here, this bulky equation, okay? You can write these Lorentz transform equation, right, as just with their index, okay? So where x prime, so this side here is the x prime, right? I want the 0th element of this, okay? I take this equation and I do this multiplication here, okay? So in this case, right, it's same as you're basically doing matrix multiplication once again, okay? Where what we're going to do is that, so this part here represents the matrix, right? So I'm going to take the 0th element of mu, okay? And the problem is that now you have a new index, right? That is the same for the x and the lambda, okay? How do you deal with that? You do this thing called an Einstein summation convention, okay? You take each of the column, right? And you multiply it to the same row index, okay? So column here, you multiply by the same row here, okay? And so the example is down here where, well, if I want to calculate what x prime 0 is, which is actually the t coordinate, right? the time prime coordinate. Okay, it turns into this equation, but then what I do with these two different nus, what you do with these two different nu is that you take the nu equal to 0, you multiply it by this x0, right, which is actually t, okay, and then you multiply by lambda 0, 1, which is nu equals to 1 now, okay, and then you multiply this by x1, right, that's not a prime, x1 is actually x, right, and then so on, and this will be x2, and this will be x3, right, which is the z coordinate. Okay. Okay. I think we should don't start the homework on this part yet. I'm gonna maybe edit it to give you guys some practice on this. Okay. This is like just based on practice, you'll see how this kind of makes. Okay. Okay. So in general, the method is that you're basically doing matrix multiplication, but then without having to write the whole matrix out, right? That's the idea. So that you can write this equation in very shorthand. Okay. Okay. So just to elaborate on this a little bit. So in general, these things are called tensors. So anything that is a matrix, a vector, technically a scalar is also a number is actually a rank 0 tensor. Okay. A vector is a rank 1 tensor. A matrix is a rank 2 tensor, and you can make rank 3 tensors out of like cubical shapes and stuff like that. But we're not going to deal with the rank 3 tensors in this class. Okay. But the main driving goal of this is to remember that equation we started up with all the way on top, equation 2.2, is that no matter which frame of reference you transform to, that number stays the same. Those are called invariants, right? Right. In fact, they're called Lorentz invariants. Okay. And the idea of this is that we want to make these 4 vectors somehow, right, do the mathematics so that they always transform. Some properties of them will always be Lorentz invariant, okay? Because what we need to do in order to do quantum mechanics with special relativity is we need numbers that doesn't change depending on the frame of your reference, right? Right? Or some variable that doesn't change, okay? So the goal is to make something that's like some dot product or a scalar product between them, like x dot x, right? That is something Lorentz invariant, okay? You already have something like this up in equation 2.2, right? Right, when we did this little diagram and calculated the time it takes for light to move from point 0 to point XYZ in some unprimed sigma frame, right? We did the same thing within the sigma prime frame, right? Right, and the speed of light is the same between them, and we came up with all these Lorentz transformation equations, right? Okay. And we define a 4 vector with the index upstairs, right? Okay. And at the time, I call this contravariant 4 vector. Okay. And we're going to see why this is going to be, there's going to be something called covariant coming out soon. Okay. So if you just want to do a normal dot product between the two, okay, right? Remember when you do a dot product, let's say of a 3 vector, right? Let's call that R. Right, x, y, z, right? If you want to do r dot r, right, that's equal to x squared plus y squared plus z squared, right? Right. If you did that with these 4 vectors, right, just do x squared, right? You're going to have t squared plus x squared plus y squared plus z squared, right? That's not what this equation is, right? That's not invariant. Right? You need that minus sign between the time and the spatial components, right? Okay, so how do we make this happen? Okay, we're going to define this thing called a covariant where the index is downstairs now, okay? And that definition is that time is the same, but then the spatial coordinates have a negative sign to it, okay? Right? Now, if you do the same techniques as what we did with the matrix with the Einstein summation, where if you have the same index on the same side of the equation, right? Right? You go through each of the index, 0 with 0, 1 with 1, 2 with 2, 3 with 3, right? And you multiply those together. Okay. since the 4 vector mu downstairs, right, has these negative signs to it, right? All the spatial signs parts has a negative sign to it, right? Now we do have an invariant, right? And this is how we deal with this, make this construction. That's why 4 vector is a little bit different from just regular vectors, right? You can have a contravariant 4 vector and a covariant 4 vector, and the scalar product of a contravariant with a covariant together, that's an invariant. Okay. In order to translate between covariant and contravariant, we use this thing called a metric tensor, specifically a flat metric tensor. So we're not going to use this too much, so don't worry about it too much. If you ever take general relativity, you have to deal with this metric that's naturally not the simple one. Okay, so once again, I'm just going to do this explicitly for you guys in 1 minute. I got 1 minute left, right? So if we define this metric tensor to be this, we can actually transform a contravariant vector into a covariant vector. Okay, 4 vector. Okay. Yeah, let's just do it quick. Okay, so remember that x mu equal to g mu nu x nu. So notice that it's placing the indices in the right place. Okay, sometimes it's upstairs, sometimes downstairs. It does make a difference. Okay. So I'm going to do this longhand just once for you guys. Okay, so remember x mu, right, is, well, I start with time. Time x, y, z. Okay, and this is going to be equal to this giant matrix 1, -1, -1, -1. Okay, and then, oops, actually I need to not have this yet, right? I'm trying to calculate what that is. Okay, t, x, y, z, zeros, 0, 0, 0. So hopefully these little squiggles are just zeros, right? When you do the matrix multiplication of this, you multiply this element with this element, right? Okay, and this actually turns into a row vector. Okay, but we don't have to worry too much about that since we're dealing with indices anyway, right? 0 times t is 0, -1 times x is -1, so negative x, so and then the rest is 0. So remember that I'm actually adding a bunch of zeros here, right? The 0 plus that, okay? Just so that it doesn't just look like I'm just copying the x over, right? Okay, similarly, the third component will get -y, the last component will get -z. Okay, and this is like, in fact, what x mu is with it downstairs, right? So you have this negative spatial coordinates instead. Okay. Right. So that's sort of the construction of creating vectors, okay, that are covariant and contravariant. And when you take the scalar product of them, they are invariant, and which is what we need in order to do special relativity. Okay. Okay. So I think I should wrap up today. So any questions before we end class?
I just want to say one thing. I'm about to send an announcement on Canvas to all of you guys, which will include a PDF of a couple chapters out of a book that I really like for its introduction to 4 vectors. So if you've never seen 4 vectors and today felt like a lot to you, then that book might be helpful. I'm also including its chapter, which is on special relativity, which I know hopefully all of you have seen before, but you know, it never hurts to have another resource.
Yeah.
So just check.
Which book is that?
It's actually, so it's the General Relativity Workbook by Moore. So it's like,
Okay.
One of the recommended textbooks for this course is the Particle Physics Workbook by Moore, which is new. This is his older book, which is on general relativity, which I really
great. Thanks.
Yeah.